Good morning, everyone. So, we'll be discussing about the surfactant mediated separation processes. And in the last class, so there are the surfactant based separation process can be categorized into three processes. One is cloud point extraction that we have discussed in detail in the last few classes, and micellar enhanced ultrafiltration and liquid membrane. In last class, whatever we did, we talked about a detailed analysis of cloud point extraction, and we have seen the design of the cloud point extractor, and we have seen one particular example how to design a cloud point extractor. Okay. Now, so we solved a problem. This problem was based on it was given that your extraction of a particular dye using the cloud point method using a non-ionic surfactant. Now, we have seen that given a particular concentration of the dye and to what extent we have to remove, suppose that concentration is known, then what is the surfactant required to separate to effect that kind of separation to that particular extent. Now, in today's class, we will first solve a problem, another problem on cloud point extractor, and then we will move on to the next topic, that is micellar enhanced ultrafiltration. Okay. So, in today's problem, again it is a problem of dye separation, because the parameters for the dye with the surfactant with the non-ionic surfactant is known to us. So, we will be again talking about a dye separation problem, but in this case the surfactant amount is given and the feed concentration is given. We have to find out what will be the dilute concentration or what is the final concentration of the dye in the dilute phase, that will give you the extent of separation. Okay. So, this problem, this example talks about a dye is removed from 3 into 10 to the power minus 4 molar concentration using cloud point extraction with 0.05 molar TX 114 surfactant at 40 degrees centigrade. Our operating temperature is 40 degrees centigrade, cloud point of TX 114 is around 37 degrees centigrade. So, we have to find out the dilute phase concentration or the dye concentration in the dilute phase. So, this is a reverse problem of whatever we have solved in the last class. Okay. So, let us look into the solution and let us write down the design equation for the cloud point extraction. The concentration of surfactant required is given as C0 minus 1 minus A Cs to the power B times Ce 1 plus n times Ce divided by mnce. This is the design equation for the surfactant concentration given a feed concentration of dye, that is C naught, and a dilute concentration and dye concentration in the dilute phase and the aqueous phase, that is Ce, and A, B etc. the isotherm Mn etc. the isotherm constants, and A, B are the properties the constants those are related to the various properties of the surfactant system. For dye and TX 114 system, the following parameters are known to us. The M value is given, which is a function of temperature. These are the adsorption isotherm parameter, minus 1.9 into 10 to the power minus 2 T plus 2.1 into 10 to the power minus 4 T square. N is equal to 1.6 into 10 to the power 5 plus 5.9 into 10 to the power 3 T minus 37.4 T square. The parameter A is given as P minus 0.11 T, B is given as R plus 0.09 T, and the value of parameters P and R are given as a concentration as a function of feed concentration of the dye. P is given as 9.4 minus 8 into 10 to the power 3 C naught plus 1.8 into 10 to the power minus 8 divided by C naught square, and the parameter R is given as 4.2 into 10 to the power minus 1 minus 2.4 into 10 to the power 3 C naught plus 2.2 into 10 to the power minus 9 C naught square. So, these parameters A and B are their functions of temperature, and the parameters P and R are the function of feed concentration of the dye. Those are given, those are known for the dye TX114 system. Now, knowing these relations, now let us proceed for the solution, given that and it is given that for this system TX114 and dye system, the value of P can be evaluated if you put the value of C naught as 3 into 10 to the minus 4 molar, and in the relations the P and R are given as P turns out to be 7.2 and R turns out to be minus 0.276. Then at temperature 40 degree centigrade, okay, the value of M and N are given, the expressions are given. So, you can evaluate that. M turns out to be 0.046 and N turns out to be 16160. Okay. So, once we know and also we know the value of C naught, that is 3 into 10 to the power minus 4 molar. So, you can evaluate the other parameters, and once you know the temperature T, you know the value of P, you can evaluate the value of A, that is 7.2 minus 0.11 into 40, that turns out to be 2.8. Just put the values in the correlations. B turns out to be minus 0.276 plus 0.09 into 40, it is equal to 3.324. Okay. Now, it is given that the concentration of surfactant in this particular problem is presented as 0.05 molar. CS is concentration of TX114, it is 0.05 molar. So, 5 into 10 to the power minus 2 molar. So, put this value into the design equation, that the design equation means into this equation, and you can, what you will be getting is this 5 into 10 to the power minus 2 is equal to 3 into 10 to the power minus 4 minus 1 minus 2.8 into 5 into 10 to the power minus 2 raised to the power 3.324 bracket end multiplied by CE, okay, third bracket closes, 1 plus 16160 CE. Okay. So, this divided by 0.046 into 16160 into CE. So, just simplify this set of equation, it turns out to be 16160 CE square plus 33.32 CE minus 3 into 10 to the power minus 4 is equal to 0. Okay. So, that gives you a quadratic in terms of CE, and if you solve this expression, you will be by using the quadratic equation, roots of the quadratic equation, minus b plus minus under root b square minus 4ac divided by 2a. So, that will give you 8.96 into 10 to the power minus 6 molar. So, this is the concentration that you are going to get from a feed concentration of dye from 3 into 10 to the power minus 4 molar to 8.96 into 10 to the power minus 6 molar. So, you will be able to reduce the concentration of dye by using the cloud point extraction from an order of magnitude of 10 to the power minus 4 to 10 to the power minus 6. So, the extent of extraction or removal will be more than 99%. Okay. So, this example illustrates you how to design a cloud point extractor. So, there are two types of problem one can face. If you would like to bring down the concentration of a pollutant from a particular level down to a particular level, then what is the concentration of surfactant you would like to require, or if you have if you select the concentration of surfactant, that is the second, there is a reverse problem, that is the problem we have solved into today's class. If you know the surfactant of the concentration, then what will be the extent of separation that you can get, or what is the concentration of the pollutant in the dilute phase. Okay. So, we close down the topic of cloud point extraction, then we move on to the next topic of surfactant enhanced separation processes, that is micellar enhanced ultrafiltration. This is a recent topic, and this topic started developing. The first paper that appeared on this particular topic, it appears in the year of early 1980s. Okay. And Professor Cameron is pioneer on micellar enhanced ultrafiltration. In fact, he has developed this topic and this particular technology, and this technology is still under laboratory research scale, and it is not it has not gone up to the commercialized or the plant scale. Okay. But the idea is you can use the surfactants in order to effect a good separation of organic or inorganic pollutants. Now, let us look into the surfactants. What are surfactants? Surfactants are nothing but the surface active agents Okay. These surfactants are there, they have the polar head groups and non-polar tail groups. That is the typical characteristics of these surfactants. Polar head group and non-polar tail. That means polar head group means they love the aqueous solution, they like the ionic environment, On the other hand, the non-polar tail, they do not like the ionic environment, they like non-ionic environment. On the other hand, you can say that these polar head groups are hydrophilic, water loving. Okay? They are hydrophilic, and these non-polar tails, they are hydrophobic, water repelling. Okay. So, these are the typical characteristics of the surfactant. In fact, in the last class when we discussed about the cloud point extraction, if we put surfactants in an aqueous solution, the surfactants will be always align themselves, surfactant molecules will align themselves across the air water interface, pointing out the hydrophobic tail towards the air and hydrophilic head towards the water. Now, there are three types of surfactants generally we can encounter. Types of surfactants, first one is ionic surfactant. Okay. They have the distinct ionic head and non-ionic tail. And non-ionic tail. The example is sodium dodecyl sulfate. Cetyl pyridinium chloride. Okay. The second one is non-ionic surfactants. These non-ionic surfactants, they are non-ionic in nature. They are entirely non-ionic in nature. That means they are always hydrophobic. Nature, example polyethoxyxylates. In fact, these are a family of various ethoxylase compounds. Third one is zwitterionic ions surfactants. They have both ionic and non-ionic characteristics. Okay. So, these are the various kinds of surfactants we will encounter. Next, we talk about the ionic surfactants only. If you remember, that when we talked about the cloud point extraction, we talked about the non-ionic surfactants only. Cloud point extraction is a process. The cloud point is basically distinctly featured by the non-ionic surfactant. On the other hand, in micellar enhanced ultrafiltration, you can use both ionic and non-ionic surfactants to remove the pollutants. But if you would like to remove the metal ions or the ionic pollutants, you must be having ionic surfactants. Now, let us talk about the ionic surfactants first. First one is the cationic surfactants. Example is CPC, cetyl pyridinium chloride. Now, these surfactants basically it will be having cetyl pyridinium group with a chloride. Now, when you put into the aqueous solution, this chloride will come out in the solution. Okay, the head group of this surfactant will be positively charged, because chloride will go away. So, head group will be positively charged. So, CPC in water, it becomes basically Cp plus Cl minus. Cl will goes into the solution. The surfactant will be having a positively charged head group. Now, second one is anionic surfactants. That is SDS. SDS is sodium dodecyl sulfate. In sodium dodecyl sulfate, you will be having SDS. When it goes into the aqueous solution, it breaks into two parts, Na plus DS minus. So, since Na plus goes into the solution, the surfactant will be having a negative head group into the aqueous solution. So, it has a negatively charged head group. So, therefore, you can have your surfactant. So, depending on the situation, you can either select a cationic surfactant or you can select an anionic surfactant depending upon your need. And what is that need and how to select the surfactant, that will go detail into the next few minutes. Then we talk about the concept of critical micellar concentration. Although we have already discussed a lot about the critical micellar concentration regarding the discussion of cloud point extraction, I would like to go into this discussion once again. As I said earlier, that when you dissolve the surfactants into the aqueous solution, the surfactant molecules will align themselves such that the hydrophilic head will be or the polar head groups will be pointing towards the aqueous solution, and hydrophobic tail groups will be pointing towards the air. Now, if you keep on increasing the surfactant concentration beyond a particular concentration, all these surfactants will not stick to the surface, they will come to the bulk of the solution having the thermodynamically favored configuration with the minimum possible energy. What is that configuration? That will be a sphere. So, these surfactants will produce spherical agglomerates of this with the surfactant monomers. These agglomerates are called micelles. Now, the concentration beyond which this particular this separation of this configuration of the surfactants will occur, this concentration is known as the critical micellar concentration. So, therefore, beyond critical micellar concentration, the surfactants will form agglomerates or globules, spherical globules called micelles. Okay. These for let us say SDS micelle, and this is a CPC micelle. So, hydrophilic head groups will be pointing towards the water environment, and hydrophobic tail group will be pointing towards the core of the sphere. So, these spheres will be having a polar outside surface and a hydrophobic inside surface. So, this core will be definitely hydrophobic, but the nature of the hydrophilic outer surface will be depending on the kind of surfactants that you are selecting. If you are selecting a sodium dodecyl micelle sodium dodecyl sulfate as the surfactant, then sodium will goes into the solution, this outer surface will be negatively charged. So, all these polar head groups will be having a negative charge residing over there. On the other hand, if you talk about if you select a cetyl pyridinium chloride micelle surfactant, this chloride will go into the solution, the outer groups will be positively charged. So, this micelle will be having the positively charged outer surface on it. Now, typically what is the fundamental of MEUF, that will be coming to later on, but before that we would like to find out what is the typical concentration of typical values of this critical micellar concentration. Typically the value of CMCs are pretty low. For SDS micelles, the value of CMC will be 8.1 millimolar. Okay. On the other hand, for CPC micelle, the critical micellar concentration will be 0.88 millimolar. So, these values are pretty low, and you can have if you increase the surfactant beyond that particular concentration, you will be getting the formation of the micelles. And what will be the typical molecular weight of the monomers? The SDS monomer will be having a molecular weight typically 288, and CPC monomers, they will be having a molecular weight around 340, and in a typical SDS micelle, the agglomeration number, the aggregation number will be roughly around 60. That means you will be having 60 numbers of these surfactant monomers in a typical SDS micelle. So, you can understand what is the molecular weight of this SDS micelle. The molecular weight of this SDS micelle will be 60 into 288, let us say around 300. So, it will be around 18,000. Okay. On the other hand, the aggregation number of CPC will be around 120. Or around 100 or around 120. So, you will be having the molecular weight of this CPC micelle will be 120 into 340, it will be roughly around 40,000 or so. Okay. Next, let us we can note typically what is the typical molecular of these micelles. They will be ranging from around 18,000, 15,000 to around 50,000, depending on the kind of surfactant we are talking about and the micellar formations and the aggregation number. And what is the typical size of these micelles? These sizes of these micelles, there is no clear cut size of this micelle. That means, you will not be having a unique peak of the size distribution. What you will be getting? You will be getting a distribution of the size distribution of various micelles. So, basically you will be getting a distribution between, let us say 2 to 10 angstrom. That will be the range of the various micelles, and I am talking about the average size of the micelles. So, you will be getting a distribution of the sizes, and from that So, that means in a solution, depending upon the concentration, you can have a micelle of lower molecular weight, as well as you can have a micelle of higher molecular weight. So, it will be a polydispersed medium, it will be a polydispersed solution. The averaging, you can average out the size, and the average size will be varying from 2 to 10 angstrom, depending on the nature of the surfactant and the concentration of the surfactant we are talking about. Now, these surfactant micelles will be larger in size, they can be separated by the ultrafiltration membrane. Okay, that is the idea. I think these will be in nanometers, 2 to 10 nanometers. They will be 2 to 10 nanometers. So, it will be in the range of 20 to 100 angstrom, that will be the range of the ultrafiltration membrane. So, ultrafiltration membrane will remove these micelles. Okay. Now, next we will talk about how to determine the critical micellar concentration, that is very important. There are several properties, those will change across the critical micellar concentration. So, if we track a particular property and track it as a function of concentration, then you will see that around CMC the slope of the curve will change. Okay. For example, if you plot properties versus concentration of surfactant, okay, the surface tension will be more or less constant, then it will reduce around CMC. Okay. The conductivity, the easiest one is electrical conductivity. I am talking about the CMC determination of non-ionic ionic surfactants. Okay. If you increase the concentration of the surfactant, the conductivity increases. Now, when it forms the micelle, the micelles will be larger in size, their transport velocity will be reduced. So, therefore, they will respond less conductivity, they will result in less conductivity. So, there is a change of slope of the conductive curve, conductivity versus concentration curve around CMC. That is the easiest way to determine the CMC, and I can tell you that this meter is very accurate with the conductivity meter that we use generally in our laboratory. Okay. Next, the osmotic pressure. The osmotic pressure increases sharply with concentration, but beyond CMC the increase will be marginal, because if you know the osmotic pressure will be pi is equal to RTC by m, it is inversely proportional to the molecular weight. So, when they are in monomer condition, so their concentration their molecular will be less. So, it will be function of linear function of concentration. So, it will increase rapidly, almost linearly, but when it forms the micelles, its molecular weight becomes more, it becomes enormous. So, it will reduce. Okay. So, therefore, that will imply a change in slope of this curve. This is the osmotic pressure relationship. So, there are, and surface tension, if you track down the surface tension, the point around which the surface tension decreases for ionic or non-ionic surfactant does not matter, that point onwards, CMC onwards, the surface tension decreases. So, if you track down some crucial properties of the solution, you can measure the value of critical micellar concentration. So, next we come to the principle of micellar enhanced ultrafiltration. Okay. Now, let us talk about the formation of the micelle onwards. So, we have let us say cationic surfactants, we have anionic surfactants. Cationic surfactants is cetyl pyridinium chloride CPC, and anionic surfactants, a typical one which is most widely studied and common is CPC and SDS, and SDS is sodium dodecyl sulfate. So, you will be having a micelle which will be positively charged in case of CPC and micelle whose outer surface is negatively charged in case of SDS. Now, the formation of the micelles are dynamic in nature. That means, monomers come and monomers go, they join the micelle and they immediately go away. So, the concentration of the surfactant, so there will be, so after formation of beyond CMC there will be two surfactant species present in the solution. What are these two? One is the surfactant monomers, another will be the surfactant micelles, and this formation of the micelle formation is dynamic in nature. That means, at every instant of time some monomers will come and join the surfactant, some will leave. Okay. So, therefore, there will be an equilibrium. Therefore, the concentration of the surfactant monomers in the solution free surfactant will be at the level of critical micellar concentration. So, if you talk about the in a micellar solution, what is the concentration of the free surfactant? That will be critical micellar concentration always. Now, if you have an inorganic pollutants, for example, if you have the metal ion means cadmium, calcium plus plus, cadmium, zinc, copper, arsenic, and then there are various metal ions like nickel, cobalt plus 2. If you have pollutants like this, these metal ions, then they will be attached, electrostatically attached on the outer surface of these micelles by simply electrostatic attractive forces. If you have the anions negatively, if you have negatively charged pollutants, for example, cyanide, permanganate, dichromate, okay, negatively charged pollutants, for example, Cn minus, MnO4 minus, Cr2O7 minus 2 minus, they will be attracted, they will be attached on the outer surface of this okay. Actually, the metal ions will be removed by the SDS micelles, anionic surfactants, because they will be negatively charged outer surface. So, if you have if you would like to remove the metal ions like calcium, cadmium, zinc, copper, arsenic, nickel, cobalt, then you have to use the sodium dodecyl sulfate micelle surfactant, whose micelles will be having a negatively charged. So, these positively charged anions will be directly attached by electrostatic attractive forces on the outer surface of these micelles. If you have negatively charged pollutants, for example, cyanide, MnO4 minus, Cr2O7 minus, they will be attached on the outer surface of cationic surfactants like cetylpyridinium chloride micelles, because they will be positively charged outer surface. Now, so therefore, what you are doing? You are basically generating large number of micelles, because if you increase the concentration, the number concentration of the micelles will increase, and therefore, you will be having large number of surface area, because the size is small. They will be in the order of nanometer, right, 2 to 10 nanometer. So, you will be having a large surface area in a small volume. So, therefore, and those points will be basically the points of adsorption of the counter ions. Okay. Now, if you have organic solvent or organic pollutants, for example, phenolic compounds like metanitrophenol, paranitrophenol, phenol, catechol, okay, there are so many, aniline, benzene. Every refinery, you can go around any refinery, the water of the close to the refinery, location of the refinery, it will be basically polluted by the organic pollutants like phenolic pollutants, benzene, aniline, all these are cancerous, right, they are the carcinogenic compounds. Now, if you these pollutants are typically organic in nature, they are typically hydrophobic in nature, and when you put the surfactant micelles in the solution, these organic pollutants will be immediately solubilized within the hydrophobic core of these micelles. So, if you have ionic pollutants, by selection of a suitable surfactants, they will be attached on the outer surface of the surfactants. If you have organic pollutants, they will be immediately solubilized within the hydrophobic core of the micelle. Now, after the solubilization of the organics or the hydrostatically attachment of the inorganics, these micelles will be slightly increased in its size, and these micelles will be having larger in size. They can be removed by the ultrafiltration membrane or more open membrane. So, what is the advantage you are going to get here in micellar enhanced ultrafiltration? The first one is, if you would like to have a physical separation process, that means you are not going to use any chemical separation process. What is the difference between the two? In chemical separation process, you are going to use some additives, some chemicals. It may be a polyelectrolyte, it may be a your coagulant or a flocculant or some other chemicals which will be added to the system, and they will form agglomerate or they will form precipitate, and you just separate them out by phase separation. On the other hand, in physical separation process, you are not going to use any external agent. By using a physical barrier, you are going to separate the species. For example, membrane is nothing but a barrier, it is like a filtration unit, okay? It is a filter, common filter. But if you would like to separate out these ionic pollutants or let us say organic pollutants, for example, phenol, aniline, benzene, they are very small in size, okay? They are not polymers, they are not big size molecule, like they are not like pectins, they are not like polymers, they are not like the proteins, okay? For example, calcium ions, they are very small in size, okay? Now, if you would like to separate these ions, then you have to go for a reverse osmosis membrane, which will be having a pore size pretty small, in the order of 2 to 10 angstrom. Now, if you remember the previous discussions, the reverse osmosis, the minimum operating pressure is 25 atmosphere onwards. So, therefore, the pump that you are going to use, it will consume huge amount of electrical power. On the other hand, if you can remove, if you can bring down the operating pressure, the pumping cost or the energy that will be involved in the process will be drastically reduced. So, therefore, all this, if you use the micellar enhanced ultrafiltration, these micelles loaded with the pollutants, arresting the pollutants, they will be separated by the membrane. So, the micelles plus the pollutants will be separated by the membranes. So, therefore, you are going to get almost a pure solution devoid of the pollutants plus the surfactant monomers at the level of CMC. But since the CMC itself is a very small concentration, that will not affect much, or if it affects, you can recover the surfactants by a separate technique. Okay. So, that is the idea, and that is the principle of micellar enhanced ultrafiltration. Okay. So, these pollutant loaded micelles, let us say they will be negatively charged, like let us say SDS micelles. The outer surface you can attach, let us say cadmium plus plus or let us say zinc plus plus. Okay. The inner core you can solubilize the phenolic compounds or organic pollutants. Now, these micelles are larger in size, they will be separated by a membrane, ultrafiltration membrane, and these ultrafiltration will be requiring an operating pressure in the order of let us say 4 to 6 atmosphere. So, the pumping energy will be much less. Reduces. Okay. So, that is the principle of micellar enhanced ultrafiltration, and so let us try to quantify various things in the micellar enhanced ultrafiltration. How much, what will be the extent of separation of the particular component, let us say anionic pollutants or the organic pollutants in case of micellar enhanced ultrafiltration, so that you can pinpoint what is the quality of my product water, or what is the second one is what is the productivity, another is the quality, one is the quality, another is the quantity, what is the productivity of the process, how much filtered you are going to get per meter square membrane area per unit time. Okay. Let us look into the quantification. Of MEUF. The first one we look into the extent of solubilization. extent of solubilizations of the solutes within the micelle, and this solubilization coefficient S is defined as solubilization coefficient this is defined as C naught minus C p divided by C naught S minus C m c. What is C naught minus C p? C naught minus C p is amount of solute that has been solubilized within the micelle. C naught is the feed concentration of the solute, the amount of solutes that you are going to have in the feed. And what is C p? C p is the permeate concentration of the solute. So, what is the rest amount? The rest amount must have been trapped within the micelle. And if you have free, because we are talking about a ultrafiltration membrane of high porosity, the pore size is much larger, and we are talking about the solutes of very low size. So, whatever the free solutes are present in the feed site, that will be easily permeable to the permeate site. So, there is no effect of concentration polarization on this particular transport of the solutes in this particular case. So, therefore, if you measure the permeate concentration, that will be same as unsolubilized free solute concentration in the feed site, because that is easily permeable. So, the concentration across the membrane of the solute is constant, that means the size is very small and the size of the pores of the membrane are quite large, around 100 times larger than this. So, therefore, C naught minus C p gives you an idea what is the amount of solute that has been solubilized within the micelle per unit volume of the solution. In micelle. And what is C naught S minus C m c? C naught S minus C m c gives you the concentration of the total surfactant in the micellar form. Okay. Concentration of micelles in terms of monomer. That means, C naught is the total concentration of the surfactant that you have given in the feed, and C m c you know. So, the rest amount C naught S minus C m c, it will be also surfactant will be having lower molecular weight, it will be freely permeable in the feed side and in the permeate side. So, across it is freely permeable across the membrane. So, C naught S minus C m c gives you an idea what is the concentration of the micelles, because the rest amount will be in the micellar form, rest surfactants will be in the micelle form, because if they are not in the micelle form, if they are in the free form, they will be freely coming to the permeate site. Okay, but that will be always at the CMC level, because micelles and the free surfactants they are always at equilibrium. Okay, so, C naught S minus CMC will be the amount of surfactants that will participate in the formation of the micelles. Okay, so, S is the solubilization coefficient, it gives an amount of ratio of amount of solute that is solubilized within the micelle per unit, the concentration of micelles in terms of monomer. Okay, it is not concentration. If you do it per unit meter cube, in both the cases it becomes to the amount. So, amount of solute solubilized per unit meter cube divided by amount of micelles in terms of monomer per unit meter cube. So, it becomes concentration effectively. Okay. So, let us write down the nomenclature for clarity. C naught is the feed concentration, of solute, C p is the permeate or unsolubilized concentration, because that is same. Okay. And C naught S is the feed concentration of surfactant, and CMC is the critical micellar concentration. Now, for single component solute system, that means, if you use different concentration of the surfactant and the solute, and if you measure the permeate concentration, so that means you can evaluate the value of solubilization coefficient as a function of Cp, this gives a Langmuir isotherm type of curve, and that will be independent of concentration, but it will be depending on the temperature. Okay. So, anyway, it will be type of Langmuir type of equation, and we can have a Langmuir type of fitting with this variation curve C naught minus C p, that is the value of expression of S C naught S minus C m C will be nothing but Q times B C p divided by 1 plus B C p. Okay. These Q and B are the isotherm constants. That means, you conduct experiments with different values of concentration and measure the value of S, and then plot with the corresponding Cp values. You will be getting a curve, then you fit a curve, and you will be getting a Langmuir type of variation. For multi-component solute, suppose you have zinc as well as calcium. So, there will be competitive adsorption. So, you will be having an multi-component extended Langmuir type of isotherm. There will be competitive absorption, and you can have extended Langmuir isotherm type equation. Okay. What are these type of extended Langmuir type of Langmuir isotherm type of equations? C01 minus Cp1 divided by C0s minus Cmc. That is, what is this? This is the solubilization coefficient corresponding to component 1, will be nothing but Q1 B1 Cp1 divided by 1 plus B1 Cp1 plus B2 Cp2. The extra term in the denominator gives you an idea what is the interaction between this is called B2 is called the interaction parameter. It gives an idea how the interference of the second component will affect the solubilization of the first component within the micelle. Okay. So, S2 similarly S2 is plotted C02 minus Cp2 divided by C0s minus Cmc is equal to Q2 B2 Cp2 divided by 1 plus B1 Cp1 plus B2 Cp2. Okay. So, this will roughly give you the amount of solubilization that we are talking about in such systems. Next, we talk about the permeate flux. So, that will give you the quality of the permeate. These isotherms will give you the quality of the permeate. What these isotherms will give? It's basically, it tells you if you know the value of C01 and C02, that means fit values of the solutes, and if you know the concentration of the surfactant, then by solving this equation you can predict, by simultaneously solving these two equations, you can predict what is the value of Cp1 and what is the value of Cp2, okay, if you know the isotherm. So, that means, if you suppose you know the isotherm for a particular system and you know the concentration of the solutes, 2 solutes or 3 solutes whatever in the feed stream, and you know the concentration of the surfactant and you know the value of the CMC, that is the property of the surfactant. Okay. So, you can solve these two equations simultaneously and can get the values of this concentration of the solutes in the permeate, and you can get the quality of the permeate. So, next you will get the quantity of the permeate, that is the permeate flux, that is the productivity of the throughput of the system. This is known as, this is quantified by J is equal to K ln Cg by C naught S. Now, it is assumed that the surfactant micelles will deposit over the membrane surface and form a gel type of layer over it, and the filtration is entirely controlled by the same as gel layer control ultrafiltration type of thing. So, at the steady state you can have the you can quantify the value of the permeate flux as J is equal to K ln Cg by C naught S as done previously. And you can find out the value of Cg, you can conduct experiment, the steady state experiment with different concentration of the feed surfactant and measure the permeate flux, the steady state permeate flux, and then plot steady state permeate flux as a function of feed concentration is a semi-log plot. Okay. Then you get a you will be getting a straight line, and if you extend the if you extrapolate the straight line, the point where it cuts the x axis, that will give you the gel layer concentration. The same way we have measured the gel layer concentration earlier in case of the protein or the polymeric solutes. So, Cg is the gel layer concentration of surfactant micelles, C naught S is the feed concentration of surfactant monomers, and Cg is basically gel layer concentration surfactant in terms of monomers, okay, and K is the mass transfer coefficient. The same way we have determined the mass transfer coefficients earlier. That means, first you have to see whether the flow is laminar or turbulent. If it is laminar, you use the Levex equation to determine the mass transfer coefficient. If it is turbulent, you can go to the Dietz-Boelter type of correlation to estimate the mass transfer coefficient. Now, determination of gel layer concentration is quite important. Of micellar solution is very important. Okay. The typical value of gel layer concentration for CPC micelles, this is around 366 kg per meter cube. On the other hand, for SDS micelles, it is 210 kg per meter cube. Okay. And we conduct experiments with various concentration of these micelles and do under same starting speed and the mass transfer coefficient, we conduct the steady, we measure the steady state permeate flux. From the plot we will be getting from the extrapolation of the data, we can get the values of these concentrations. Now, once you have this concentration, then you will be able to predict the quantitatively what is the permeate flux or the filtration rate. Now, in presence of the counter ions, there are several complicated phenomena, those will occur during micellar enhanced ultrafiltrations. Those will affect the performance of the system. In fact, we will be discussing all these effects in detail in tomorrow's class, and we will be solving some of the problems to quantify how to quantify such systems in detail. Okay. So, we stop in today's class and we will move into the next class for further discussion on this particular topic. Thank you.